So now that we've talked a bit about what parallelism is as a concept, we've talked a little bit about how Java supports parallel computing, let's talk briefly about the history of these technologies of both concurrency and parallelism in Java. Java has been around for a long time, and so it isn't surprising that it has many different features that have evolved as the community of programmers, community of people building Java, the community of people building hardware have matured over the past 25 years or so. You might know some of this stuff, but it's worth kind of recapping it because depending on where you go and what you do, you may be stuck in some of these paradigms. I was talking after class to some folks who were like, the company we worked at over the summer didn't support modern Java. We were stuck using legacy Java. And, what a shame. The answer is yes, that's a shame. There's lots of stuff that's very cool that's in modern Java that is much more awkward to do in traditional classic Java. So this will give you a little tour through how things evolved over time. So when Java first came out, which was the mid-90s or so, it evolved from a language called Oak, developed by James Gosling, who was then at Sun. It supported threads, and it supported so-called built-in monitor objects. So since day one, Java has supported the concept of concurrent programming. And the focus in those early days, because we didn't really know much better at that time, and the hardware and the software was not as sophisticated, the focus in those days was on basic multi-threading and synchronization primitives. Very simple stuff. So here's a small example to kind of illustrate this point. Here we're going to have a pair of threads, a producer thread and a consumer thread. They're going to share a so-called simple blocking queue. You can get the source code if you want to see what this stuff does. And we're going to spawn those two threads. So they're going to be created. They're going to communicate together through this bounded buffer, which is what the simple blocking bounded queue is. And then we're going to go ahead and start the threads by saying for each thread in the threads array, start the thread. That'll set the wheels in motion. Processing will take place in the background. The two threads one thread will produce, the other thread will consume through that shared queue, shared buffer. And then when they're all done, or actually after they start, we're going to go and wait for both threads to finish. And this join operation here is a very simple barrier synchronizer that waits for all the threads to complete. So we start the threads and then we join the threads. So that's a very simple example of threading. Here's a very simple example of synchronization using fundamental Java synchronizers like mutual exclusion and coordination primitives. So in this particular model, it says the take method is only going to allow one thread of control at a time to be executing in its critical section. And we're going to synchronize on this, which is just the object that take is being called on. And that means only one thing at a time is allowed in this critical section. And then while the list is empty, because we're trying to get an element off the list, off the thread safe list, or basically a synchronized list, what we're going to do is while the list is empty, we're going to wait. And wait is going to suspend this thread until someone comes along and notifies it that there's something in the list or in the queue that will then allow it to wake up and make progress. And we're going to say, we're going to notify everybody that we're going to wait here until we've managed to get an element, or until there's an element in the list. Then we're going to notify anybody who's waiting for the list to be not full, because we're just taking an element, and then we return the front item on the list. So again, without getting too much into the details of synchronization, because that's not the focus of this course, these are some simple examples of synchronizers in Java 1. So if we're going to analyze this particular approach, it's efficient in the sense that it's very low level, it's close to the hardware, it's close to the operating system, the underlying machine that's doing the processing, but it's very low level and very limited in what you can do. There's all kinds of opportunities for accidental complexities. And accidental complexities are problems that arise from limitations with software techniques, tools, and methods. So race conditions, issues with deadlock, other problems of inefficiency and so on. Those are the problems with programming in that style of Java. So because of the limitations with Java 1, when Java 5 came along, which was roughly the 2004 timeframe, so 15, 16 years ago, they added a whole slew of new concurrency and synchronization frameworks and mechanisms. So they added something called the Java executor framework, which supports coarse grain task parallelism. They supported a whole bunch of synchronizers like reentrant locks and things like condition objects and semaphores and so on. They supported blocking queues like array blocking queue, linked blocking queue, and so on and so forth. They added support for atomic operations, which allows you to be able to set variables and check variables in a way that's atomic and very efficient. And they also added support for concurrent collections, things like concurrent hash map. So these all became available in Java 5. As I mentioned, the focus was on coarse-grained task parallelism. So rather than having, millions of things, which is what we got with the fork join framework, which we'll talk about in a second, the focus in Java 5 was on fairly coarse-grained tasks. And the reason that they did that was at the time, 2004 timeframe, most processors had 2 cores. That was like the typical amount of parallelism. They didn't have the kinds of processors we have today with 8, 16, and more cores. So there weren't that many things you could really do, so you focused on coarse-grained processing with a relatively small number of tasks, and tasks were what ran concurrently. And so you would submit a task, and it would go into a queue, and then there'd be a pool of threads that would run and take things off the queue and do some processing and put the results back somewhere that they could be obtained by a client once the work was done. So this basically allowed tasks to run concurrently at the same time, taking advantage of the parallel computing resources in those days. Here's a very simple example. This is actually not unlike a program that you'll do if you come back to my sibling course in the spring, where we're going to implement a Palantir manager app, which is super fun. And we go ahead and we create a pool of threads, typically a fixed size pool of threads. And then we go ahead and create a couple of barrier synchronizers, which will coordinate the starting and stopping of those threads that are running in the pool. And then we go ahead and give the thread something to run. And again, you'll have to come back for the class, but we basically have a really cool visualization in Android of beings from Middle-earth, right? So hobbits and wizards and dark lords and stuff like that. And they go ahead and run, and they contend for a limited number of Palantiri, which are mystical seeing stones that allow you to communicate over great distances. Anyway, I'm a Lord of the Rings fan, as you'll find out. So it was just a fun way to show off a bunch of cool features from Java 5 and other technologies. Java 5's concurrency mechanisms were very feature-rich, very optimized, very clever, but also, honestly, tedious and error-prone to program, because programming with synchronizers, programming with tasks can be difficult because there's lots of accidental and inherent complexities lurking in that space. Because of that, Java 7, which came out in the 2010 timeframe, added foundational support for parallel computing. And what they added, which we talked about briefly in an earlier video, was support for the fork join pool. So Java 7, 2010, fork join pool. And as I talked about before, that was fine-grained data parallelism as opposed to coarse-grained task parallelism. So the idea was, as I mentioned before, you take a task, you take data, and you split it up into little chunks, and then you go ahead and process it. And so the idea there is it's a lot more scalable, and you don't have sharing, so the need for synchronization goes away, and so on. And it typically uses that divide and conquer approach we talked about, which is the split, apply, combine model, which is used for forking and joining things and running them in parallel. Under the hood, with Java 7 came the concept of the fork join pool. Then in Java 8, they had this concept of the common fork join pool, which is a common pool that's used if you don't want to create a separate custom pool. You can just use the common pool and do all the processing in parallel there. And there's actually good reasons we'll talk about later why the common fork join pool is the one to use, because by putting as many concurrent tasks in one place, it allows the work stealing algorithm to work most effectively, because you have lots of things to work on. So Java 7 support, and then later Java 8 support for the fork join pool and the common fork join pool was very powerful, very scalable, but still tedious to program, because we had to be responsible for the forking and the joining. And it was an object-oriented approach. It was a little bit crufty. It required knowing how to do inheritance and overriding of methods. And so as a consequence, it was somewhat difficult to program in practice, even though it was very powerful. So what happened in Java 8, and you can kind of see the progression, it's really cool. They said, well, we've added a whole bunch of cool features in Java 8 having to do with functional programming. things like lambda expressions and method references and functional interfaces, all the stuff you can learn about if you watch my playlist that I sent you out in one of the early emails. So they took those concepts and they wrapped them around the fork join pool and thereby created this advanced functional programming framework mechanisms, 2 of them, in Java 8. So they have parallel streams and completable futures. We also talked about those briefly, so I won't dwell on them here. But basically, this is fine-grained functional programming for data parallelism, which is what parallel streams provides. So you can have a bunch of threads that will transparently process data as it flows through the operations in the stream. And then they also added support for so-called reactive asynchrony, which is what you get with completable futures. So that gave you the ability to split things up into small chunks and then reassemble them. And it's actually also, here's a very simple example of how to do this. This is a parallel stream that's going to take each element in a list of URLs, find the ones that haven't already been downloaded, cached, and previously processed. It'll download the non-cached ones. It'll apply a bunch of filters to them, and it'll then collect them up into a list of filtered images. It's actually possible to combine streams and completable futures together, so you can do a lot of things in parallel with asynchrony. This is a really, really cool model. We'll talk briefly about it when we get to that later in the course, where you use streams to structure the flow of control, and then you use completable futures to do the processing asynchronously. It's really, really cool. So something else that came later in Java 9 was the support for reactive streams. And so what that does is it basically takes some of the concepts from parallel streams and completable futures and merges them together into a single programming model that supports the propagation of changes and the ability to be able to stream things together and connect them. So it's very, very cool combination of both. And here's a simple example that uses the mechanisms from Project Reactor to do the same concept of downloading a bunch of images and so on and so forth. So we'll talk about this stuff later. So one thing to keep in mind with all the things we just talked about, especially the later features that came into Java, is that they're trying to strike an effective balance between productivity, which is making people more productive, making people more efficient, and better performance, which is about making computers work better or using the power of computers more effectively. Historically, there have been kind of 2 choices. You could either make things that were easy to program, like a single-threaded application, but they don't scale very well, or you could make something that was very scalable, but which unfortunately was hard to program. So that's what we've dealt with up to this point, or this point being the last decade or so. With the introduction of modern Java, you can get the best of both worlds. Often you get highly scalable performance that's also much easier to program. And you'll get a sense of this, actually you'll get a literal sense, a visceral sense, when you implement Programming Assignment 1A. Programming Assignment 1A uses sequential streams, which means that it's using the streams model, but there's only one thread of control. And what you find when you run your code, and when you run it and look at the GUI, you run it in your emulator, it takes a long time to download and transform each image one at a time. When we go later to parallel streams, which we'll do in assignment 1B, and if you have a multi-core processor, which you most likely do, you'll see it runs way faster. So if you have 4 cores, it'll run in a quarter of the time, basically, because it's an relatively embarrassingly parallel program for the assignment. So that'll give you more experience kind of trading off between performance and productivity. So Java's trying to thread that needle to give you the best of both worlds. There are, of course, some downsides. There's always downsides to everything. These frameworks give you a lot of structure, but sometimes they box you in a little bit more than you might like. That's rarely a problem in practice, but it's just something to be aware of. Brian Getz, who's the chief architect for Java, the Java platform, has a really good talk that discusses the evolution of Java from concurrent to parallel computing. And you can watch that here. It's a really, really good talk. I strongly recommend you watch it. And he's the one who really talked about this N times Q model and talks about how Java 8 combines functional programming with fine-grained data parallelism in an attempt to try to take better advantage of processor cores. And so here's the situation they were trying to address with this. You would think as the number of cores goes up, performance would go up just as fast as the number of cores. But that really hasn't proven to be the case, and that's because using the traditional ways of programming parallel computers, things like task-based concurrency is very complicated. So the effort to introduce data parallelism with a functional facade or a functional veneer was really the motivating force with Java 8 and beyond, modern Java, to make it easier to program things that would take advantage of the hardware parallelism. There's also a great video by Rob Pike, who was a famous contributor at Bell Labs in the Unix and Plan 9 days, and then I think he's at Google now. He's kind of the driving force behind the Go programming language. So if you know anything about Go, he's one of the movers and shakers there. And he has an interesting talk about how concurrency is not parallelism. And he differentiates these things by saying concurrency is about dealing with lots of things at once, whereas parallelism is about doing lots of things at once. And that's a reasonably good definition. Everybody has their own definition, but basically the main thing to remember is that with parallel computing, when all goes well, things really are actually running at the same time. With concurrent programming, they might be running at the same time, but typically not in the same way that parallel computing is. Concurrency is often more about sharing information in a reasonable way, avoiding various hazards. So that's the end of our quick tour through the history of concurrency and parallelism support in Java.